Citizens and solar cooling.
Thank you. Thank you for the introduction, and also thank you for the introduction for the prior speaker who already introduced the topic solar cooling and regeneration, because the title of our paper is called Energy Efficient Cooling with Absorption Chiller Technology in Solar Cooling Systems, but also CHPC-Plants, that is Combined Heat and Power Cooling Plants, which stands for regeneration. So I'm here presenting our paper from our university, and the head of our institute is Professor Ziegler, Felix Ziegler, some people might know. What are we going to talk about today? I'm going to introduce some projects in the beginning, then move over to the absorption chiller control that has been implemented in the chillers, and also the extensions that we've implemented in the last months. Then I will go over to the monitoring and the hydraulic concepts on a very broad scale. And then I would like to show you some operational performance results that we have gained in the last years. And then I would like to conclude. So, field test regeneration is the bigger project that we have in Germany. This has a very German title, which we abbreviate with FATS. It deals about 15 field tests throughout Germany here, as you can see. In total, there are 25 absorption chillers installed. And the aspect of regeneration is always there, because sometimes we have cooling, heating, and electricity supply. We are doing research and optimization upon the fields of construction of the chillers, system integration, and last of all, and most important, the control concepts, not only for the chiller, but also for the interaction with the system. And also about the topics of supply security, because it's a very important issue here. We have been doing a detailed monitoring ever since the commissioning that started mainly in 2013, and the last chiller that was commissioned was this summer. The project is supported by the Federal Ministry of Economics, and we have several research partners here, and also in those locations 13 field test partners. A smaller project, solar cooling, it's called Solar Cooling Industry and Commerce. It's supported by the Federal Ministry of Environment, Natural Conservation, Building, and nuclear safety. It deals about 4 solar cooling installations in Jordan. And in comparison to the former project, it not only deals about the installation and commissioning, but also about a certain knowledge transfer and the promotion of the technology in the MENA region. So we are taking a consulting role there, but throughout the planning, the procurement, the installation, and the operation phase. We are directly in the field of local capacity building and personal training on the site. And we've been doing the commissioning ever since 2015 of those 4 chillers, and since then the monitoring. The project has now been ended, and it was under the lead of the GIZ, it's the German Agency for International Cooperation. So when I talk about absorption chillers, there are 2 types of chillers that we have developed and brought into the market with a manufacturer. They are called Beak and Bumblebee, funny names, but it applies to their capacity. So the Beak can provide 50 kilowatts, the Bumblebee 160, at a rather good COP, not to say outstanding COP, but keep in mind that they are providing chilled water at a high temperature level, 21 to 16, and cooling down the hot water from 90 to 72. The working pair, again, is water as a refrigerant and lithium bromide as a sorbent. And of all those chillers, there is a total amount of 2.7 megawatt installed in all those installations. This is the design capacity, not the nominal capacity. And 60% more or less is office cooling, and the remaining 10 to 15% go into hospital cooling, process cooling, and IT center cooling. Here you see that there's a quite broad range of what temperatures is to be provided by those chillers, starting from 6 degrees, that is interesting for dehumidification systems and HVAC systems, up to 16 degrees for IT centers. Also, you can see that there are systems that are providing up to 400 kilowatts. This is a combination, sometimes of a bee and a bumblebee, sometimes also of multiple bumblebees. I would like to show you very, very shortly how the absorption chiller is operating. As you know, there are 4 main heat exchangers. This is the evaporator, the absorber, the dissolver, or the generator as we had before, and the condenser. On the left side, we have those two heat exchangers, which is basically the same as in a compression chiller. We're using the effect, the thermodynamical effect of water that is able to evaporate at a very low pressure. So inside the chiller is almost vacuum, and when we have the external chilled water circuit here at 21 degrees, it can transform the liquid refrigerant into vapor, which then gets into contact in the absorber with the concentrated solution, is diluting it, and this one is pushed up to the dissolver where it's been cooked out. And the solution is again concentrated. And then we have steam going to the condenser, and in those processes, absorber and condenser, we have, due to the dilution and to the condensation heat, we have abundant heat that has to be injected. Whereas in the generator, we have to provide the chiller with a driving heat source. That can be a solar field, that can be a district heating system, and so on. So the control, as you saw before, here's the chiller as a black box. And it needs to be controlled so as to supply a cooling demand, or supply cooling that matches the cooling load. The cooling load can be defined as a volume flow multiplied with the density and the heat capacity and the temperature difference that it has to cover. And this one has to be supplied here at the evaporator circuit. In order to do that, we have to operate a pump in the dissolver circuit and the freeway valve, and a pump in the cooling water circuit, and also a dry cooler. All of these actors have to interact in some way. So the common control that is usually used in the market is using this valve here to control the inlet temperature in the dissolver, because there's a linear correlation between the output and the absolute temperature. And usually in those cases, the inlet temperature in the absorber is constant. Let's get over to the absorption chiller control that is implemented in the field test. This is based upon the CE control. This is the characteristic equation system, which has been developed by Professor Ziegler. And this takes into account that there is a characteristic temperature difference that can be applied to every heat pump in the market. And by knowing the external temperatures and the construction of the chiller, one can easily say at what temperature the chiller has to be driven in order to supply the cooling load. So the inlet temperatures of the dissolver and the absorber are set values that are regulated simultaneously in order to provide the cooling load, in order to cover the output temperature here at the evaporator, and also sometimes, especially for CHP systems, provide a certain output temperature at the dissolver so that the CHP system is not shutting down. The chillers are fully automatic, and they are autonomously controlling their internal and external actors, all the actors that you can see here, and it's power controlled and intrinsically safe. So let's get over to a brief simplified PID, process and instrumentation diagram. We have a lot of field tests, a lot of complex systems. I've tried to broken them down to a very easy one so that you can understand the results in the end of what we're talking about. So again, we have the absorption chiller that is providing cooling, and we need a high temperature heat source that can be a solar energy and so on in order to drive it. In this case, we're talking about absorption chiller cooling. When the absorption chiller is not enough, or there's a backup system needed, or there's another compression chiller needed, we're talking about compression chiller cooling, that is also feeding the network here. And due to the fact that we have a water-run absorber condenser circuit, we can utilize this dry cooler in order to provide free cooling in winter time or in the spring or autumn time. Because the temperature here on the outside is sometimes lower than the temperature that is needed here. So instead of operating all those actors, one can simply transport heat through these heat exchangers, which is only needed if we have here a glycol, which can also be left apart. So the monitoring of the system, here again you see a very simplified mode, and this is only the sensors that are related to the energy evaluation. There are also other control sensors, etc., that are not shown here. And we see that for all process-related actors and all boundaries, there are heat flow meters consisting of two temperatures on return and supply, a volume flow sensor, a calculating unit, and watt-hour sensors for the electrical components, and all those data is being acquired and is being analyzed. So let's come over to the extension of this absorber control. There are multiple strategies that we are trying to practice now in the next time. I will introduce only 3. The first one is controlling this pump so that the volume flow here matches the volume flow of the building, because the volume flow of the building is fluctuating due to different consumers, etc. So the chiller can operate much more efficient in a particular condition. Second strategy is changing the flow here by having the goal to operate the pump so that there's a constant temperature difference here. Also, again, in part load conditions. As you will see later, the electricity consumption will be reduced dramatically. The last one that I will be showing here is a set point temperature for the dry cooler. So this set point temperature sometimes goes below the ambient air temperature. In case of dry cooling, it does not make sense to operate the dry cooler at 100%, because in between 70 to 100% of the speed the dry cooler can provide, there is no change in the output temperature. So in this case, again, the dry cooler can become more efficient. Let me give you now a short performance result of how the chiller operated when we activated the second strategy. We see here a running day in December last year, and we see here that the cooling load of the building is at 10 kilowatts. The temperature inlet and outlet of the condenser leads to a difference of 2 Kelvin, and the volume flow is here at 40 cubic meters per hour, and the COP, the electrical efficiency, is at a low level of 4. So then, at 8 o'clock here, 2 effects take place. One, the cooling load is increasing, goes up to 20 kilowatt, which is successfully covered by the Absorption chiller. And the second effect is that the strategy is being activated, leading to a decrease of the volume flow by keeping this temperature difference that is fixed at 6 Kelvin constant. As a result, you see that the COP is increasing to 16 and is being kept constant throughout the night and the following days. So this is a very efficient way of reducing the consumptions in the region heat circuit. The energy performance figures, which you probably know, are introduced in the paper, so I will not be going there into detail. Keep in mind there's a difference between electrical and thermal efficiency. And let's get over to the evaluated sites in the paper. So we're talking about 8 absorption chillers connected to district heating. They are called D1 to D8. Then 3 systems or 2 systems with 3 chillers concerning CHP systems. They are called C1 to C2. And last of all, 3 solar systems, solar cooling systems, they are called S1 to S3. So in terms of operativeness, availability, and how much the chillers were in operation, I try to show you here in descending order how much of this regarded time period, that is January to September 2017, January 2016 to September 2017, I would like to show you the cooling operation of this chiller, for example, operated almost at all this time, due to having a cooling load that is 24/7, 365 days a year. And then you see descending cooling operations from the other systems, which are which can be due to the fact that there is no cooling load in those buildings, they have less operating hours. Some chillers had maintenance, were out of service, because there were software updates, there were failures in the external actors and so on. But nevertheless, 80 to 100% availability was given. So the chillers were, let's say, 100% available all the time, which is important if you're cooling down a circuit in the IT center. The same can be said about the cooling work. We see that we have in total 4.8 terawatt hours of cooling provided. Certain amounts were provided extra to those 4.8 terawatt hours by compression chillers, and some amounts were contributed by free cooling. So let's come over to the electrical efficiency, because my time is getting thin, which is, let's say, one of the most important slides. Here again, the sites over the electrical COP, or the reciprocal of that, that is the specific electrical consumptions. we see in this diagram for all sides three main things about one plot here. That is the mean value, that is the cross. The blue box is representing 20 to 80% of the spread that we have in the values, and the other line is representing 5 to 95% of the daily values that have been calculated. So we see here that in total, the systems are operating in between 5 to 32 kilowatt hours of cooling per electricity. If we go and compare that with the compression chiller, which is operating here at a higher electrical consumption or in a lower COP, as you can say, we see that, for example, even the highest, the most efficient model here is providing an electrical COP of 4. That means that the absorption chiller can provide 6 times, 7 times more than the compression chiller system in this field case. The thermal efficiency for the absorption chillers are varying throughout the field test. Some are quite outstanding because we're reaching values of over 0.7, and some have less values due to being operated in strong power load and having internal optimization problems that we're dealing with. I think our time is almost over.
You can have it from the next one.
Okay. So maybe you remember the second strategy that was volume flow control of this pump here. What is the outcome if we operate that with different set points? Set points meaning this temperature difference here. I selected 2 sites that we implemented those control strategies in the last months. On the right side, a field test with a very volatile cooling capacity on the right side. On the right side, a field test with a very constant cooling load as it was in IT center. So we see, for example, here the black dots are indicating that the strategy is inactive, and once the strategy is being activated and we increase the temperature difference, decreasing thereby the volume flow in this pump here, we decrease dramatically the specific energy consumption in this circuit. Same can be seen here, where we have a little bit more fluctuating cooling load, but in the end, the outcome is the same. It follows a little bit more the characteristic of the cooling load in the site, but nevertheless, we see that with increasing temperature differences in the cooling water circuit, the specific electrical energy consumption in the circuit is decreasing again. So it's a very promising strategy. Also, other strategies are quite promising. And as I introduce now, again, some sites that I selected, those 2 we saw now in slide 4, and another 2 for solar systems. We saw in the values before for the electrical COP that you can reach here 14, 4, 3, 6 for different reasons in the standard control without any activated control strategies. In the last months, as I mentioned, we activated different strategies, mainly strategy 2, meaning volume flow control in the BJP circuit, sometimes also the dry cooler, but mainly the second strategy is responsible for the decrease of a specific consumption. In other words, the increase of the efficiency, electrically speaking. So we see here, for example, we can have again a spread, and we can increase on average the electrical efficiency from 14 to 24, from 4 to 11, from 3 to 4, from 6 to 8. So it is quite promising, the strategy. Also, in combination with other strategies, especially the one here, strategy 1. But those results will be given in the next years, I guess, because this is only the beginning. So I would like to conclude. We saw that absorption chiller cooling is possible with different high temperature heat sources. These are heating systems, which are quite common in Germany. I heard also they are common in Greece. Combined heat and power plants, which have their own demands, a fixed temperature difference at their hot water circuit, and also solar systems, which, as we saw in the slide before. We saw that the operation of those absorption chillers is successful and stable. In the last years, we only saw the monitoring points from 2016. In total, we are dealing with 29 absorption chillers, 15 in Germany, 4 in Jordan. The electrical efficiency of those systems is reaching values of 30. This is quite a number. The thermal efficiency can reach values of up to 0.8. That is the nominal point as was promised in the data sheet. And this is very important for those companies or those buildings that have to have the security that they will get cooling out of this chiller here. Means that there's almost 100% availability, not to say 100%. Also, the application of the control strategies, as we saw a little bit here, can lead to reduction of electrical consumptions and increase of the electrical efficiency. Last of all, one has to say, we can even increase more the electrical consumptions if we start making tailor-made controls. It means that this unit needs a little bit more of that, and so on. So it's going to be interesting for us. I hope I have raised a lot of questions on your side, or the interest in the field of solar cooling and generation systems, and I'm open for questions. Thank you.
Thank you.